We are the group to present variable underflow. This group consists of 4 students, namely Endonto Joseph, Escalante Cherise Hope, Lasarte Rover Neil, and Makauba Paula Aliyah V. So we first need to know what underflow is. So an underflow is the desired material dissolves to some extent and so leaves when the liquid is thrown off as overflow. The solids are then removed as underflow. Because the underflow is wet, some of the solvent or solute mixture is also taken out here. A leaching system's flow can either be cross-current or counter-current. We have here a flowchart of the process of leaching to better understand it. First step is leaching, to remove or remove from by the action of a liquid passing through a substance. Under leaching, it has two branches. The batch leaching, which is a leaching test that estimates how readily contaminants could mobilize out of a solid waste or other material if the material comes into contact with natural waters. And continuous leaching, which process of leaching by the use of continuous equipment in which the solid and liquid are both moved mechanically. Continuous leaching can either be cross-current leaching or counter-current leaching. For counter-current leaching, it has two branches, the constant underflow and the variable underflow. Variable underflow. The operating equation for leaching is not linear if the solution underflow is not constant. The underflow vary from stage to stage, thus a modification of McCabe-Thiele graphic method may be used for calculation of the number of stages. It causes to more requirement of the solvent in the process, thus more number of stages.
If the density and viscosity of the solution change with x, solid from lower number of stage retain more liquid, that is L1 is greater than L2 and so on. For the slope of the operating line varies from unit to unit. So in variable underflow, operating line passes through XAYA and XBYB. If the flow rate is constant, we can then use L over V for the slope. So for the number of ideal stages for variable underflow, first we are going to determine the terminal points XAYA, XBYB by material balance. And then we are going to find the intermediate point. So for xn here, we are going to choose L as function of x. Then we're going to solve for Ln, then overall mass balance to get Vn plus 1, then mass balance to solute to get Yn plus 1. So this is the formula. So this is for the overall mass balance, and this is for the mass balance to solute. And to be able to get the value of Yn plus 1, we are going to use this formula. After solving for the values, we are then going to plot the operating curve, that's XAYA, XN, Yn plus 1, then XBYB.
In solving variable underflow problems, the three equations must be considered. First is the total solution balance, where in terms of L sub 0 is equal to V sub n plus 1, which is equal to L sub n plus V sub 1, which is equal to M, where M is the total mixture flow rate in kilograms A plus C per hour. Second is the component A balance, where L sub 0 is multiplied to YA sub 0 plus V sub n plus 1 multiplied to X sub n plus 1, which is equal to L sub 0 times Y sub an plus V sub 1 multiplied to Y sub a1, which is equal to M sub X am. And the third, which is the solid balance, where in terms of B is equals to N sub 0 multiplied to L sub 0, which is equal to N sub n plus L sub n, which is equal to N sub n multiplied to M, where nm and xam are the coordinates of point M as shown in this figure. Usually, the flows and compositions of L sub 0 and Vn plus 1 are known, and the desired exit concentration of Y sub An is set. Problem. A continuous countercurrent multi-stage system is to be used to leach oil from mill by benzene solvent. The process is to treat 2,000 kilograms per hour of inert solid meal of B, containing 800 kilograms of oil of A and also 50 kilograms benzene of C. The inlet flow per hour of fresh solvent mixture contains 1,310 kg benzene and 20 kg of oil. The leach solids are to contain 120 kg oil. Data are tabulated below as n kg inert solid B over kg solution and Y sub A kilogram oil A over kilogram solution. The required of this problem is to calculate the amounts and the concentrations of the stream leaving the process and the number of stages required. So as you can see, these are the tabulated data that are given in the problem. So this is the mass balance diagram where the feed slurry and the entering solvent A, B, and C are given. And as you can see in the underflow solution L sub n, only the value A and B is given while C is unknown. So in solving this problem, first is that we find the coordinate at L sub 0, which is the feed slurry. And as you can see, the mass of A, B, and C are given. So in getting the coordinate for L sub 0, we must find the value of Y sub A sub 0, which is in the form of A over L sub 0, which is equal to A over A plus C. And as you can see, A here is 800. And A plus C is equals to 800 plus 50, which is 850. So 800 divided by 850, which is equal to 0.24, which is the value of Y sub A sub 0. And next is to get the value of N sub 0, which is in the form of B over L sub 0, which can be computed by using the formula of B over A plus C. So the value of B, which is 2000 over 850. So 2000 divided by 850 is equal to 2.35. That is the value of N sub 0. So the coordinate for the feed slurry is equal to Y sub A0, which is the x coordinate, and N sub 0, which is the y coordinate. So the x coordinate is 0.94, while the y coordinate is 2.35. So next is to find the coordinate at V sub n plus 1, which is the entering solvent. And as you can see, the mass of A, B, and C are given. So in order to get the coordinate for V sub n plus 1, we are going to get the value of x sub n plus 1 and n sub n plus 1. So in getting the value of x sub n plus 1, which is in the form of A is equals to V sub n plus 1, which can be taken from the formula of A over A plus C. So as you can see here, 20 is equal to A. So 20 plus 1,310, which is equal to 1,330. Then 20 divided by 1,330 is equal to 0.015. So the value of x sub n plus 1 is equal to 0.015. And in getting the value of n sub n plus 1, which is in the form of b over v sub n plus 1, which is also in the form of b over a plus c, where 0 over 1,330. Then the answer is 0. So the coordinate for v sub n plus 1 is equal to 0.015 and 0. So the next step is to find also the coordinate at L sub n, which is the underflow solution. And as you can see here, the mass of A and B are given, while the mass of C is unknown. So in order to get the mass of C, we have taken this formula n sub n over y sub n is equal to B over L sub n divided by A sub L sub n, which is calculated in the form of B over A, which is B is equal to 2000 over 120. So 2000 divided by 120 is equal to 16.67. So n here is 16.67y. Then if we assume that y is equal to 0.1, then n is equal to 16.67 multiplied to 0.1, then the answer of n is equal to 1.67. So by plotting the new coordinate y and n, so x coordinate is equal to 0.1 and y coordinate is equal to 1.67. So here is the graphical representation of L sub n, V sub n plus 1, and L sub 0. After getting the coordinate of the feed slurry, entering solvent and underflow solution, we proceed to the next step, which is the total solution balance, which is introduced in this form that is presented in the past slides. So L sub 0 is equal to V sub n plus 1, which is equal to L sub n plus V sub 1 is equal to m. By deriving this formula, we arrive at this formula where L sub 0 plus V sub n plus 1, which is equal to m. So we know that the value of L sub 0 is equal to 850 and the value of V sub n plus 1 is equal to 1330, which is equal to m. To get the value of m, we add the value of 850 plus 1330, so the value of m is equal to 2180. So by using the component balance, we arrive at this formula. So L sub 0 times y sub a0, which is 850, and 0.94, and the value of v sub n plus 1, which is 1330, and the value of the coordinate of x sub n plus 1, which is 0.015, and the value of m, which is 2180, to get the unknown value of x sub am. So by multiplying and adding, we get the final value of x sub am, which is 0.376. Next is to get the solid balance. So by deriving this formula, we have arrived at this formula, where n sub 0 times L sub 0 is equal to n sub m multiplied by m. We all know that the value of n sub 0 is equal to 2. We all know that the value of n sub 0 is 2.35 and the value of L sub 0 is 850. So in getting the unknown value of nm, so we multiply the value of 2.35 times 850 divided by the value of 2180. So the final value of nm is equal to 0.916. So the coordinate for m, which is x sub m and nm, is equal to 0.376 and 0.916. So in plotting the coordinate m in the graph, we have to construct line from point Ln to point M until it crosses at x-axis, and the point at x-axis is equal to v sub 1. So this is the second graphical representation where we insert the value of the coordinate for v sub 1, which is x sub 1 and n sub 1, and the coordinate for L sub n, which is y sub 1 and n sub 1. So as you can see here, this is the new values that we inserted, the color red. So the next step is to assume the equation where v sub 1 is equal to 2180 minus Ln, which is in the equation 1. So by getting the component balance, L sub n times 0.12 plus v sub 1 multiplied to 0.592, which is the value of x sub 1, and the value of m, which is 2180, times the value of x sub am is equal to 0.376. By inserting this equation to the equation 1, which is this, so we have arrived to these equations. By multiplying the equations, this is the equation. So by adding the equation and multiplying, we have arrived to this point. So 470.88 divided by 0.472, we have arrived at the final amount of L sub n, which is Ln is equal to 997.62 kilogram. and lastly, we insert the value of ln to the equation 1, where ln is equal to 997.62. So v sub 1 is equal to 2180 minus 967.62. So by subtracting the two values, we have arrived at the value of v sub 1, which is 1182.38 kilograms. And by connecting the value of L sub 0 with V sub 1 and L sub n with V sub n plus 1 and the cross line, which is the operating point, we have arrived at these graphical representations. So as you can see, we add the value of L sub 1, L sub 2, L sub 3, and L sub n. And at this point, you can see that it is 4 stages. So this is the final graphical representation of the variable underflow. Thank you for watching.